Hey everyone, welcome to the lecture on exploring Mars. This is going to cover essentially the exploration of Mars, the robotic exploration of Mars. That's all we've done so far, um, from roughly the space race to now. But you'll remember in the space race we talked briefly about some of the missions that were sent past Mars, some of the Mariners. We'll revisit the Soviet Mars missions and the Mariner missions, but then we'll jump into kind of the serious exploration of Mars. Not that the Mariner missions didn't accomplish great things for their time, but by modern standards, they're very limited in what they sent back. And it really picks up with the Viking missions in the 1970s, bit of a quiet period in the 80s, and then in the late 90s, 2000s, and certainly the last decade, lots of activity at Mars. So this is going to cover as all the lectures do, a time span to the present and including the present, with two major active rovers still on Mars, one that just only recently stopped working in the summer of 2023, the Geology rover. And we won't cover every single mission that's ever been to Mars. Once upon a time, we used to do that in this course, but it's gotten to the point where such a lecture would be 3 4 hours long, and it's just too much. So I focus on some of the big ones, some of the major ones, and I think it gives you the full picture of what we've learned about Mars through robotic exploration. And with this week's podcast and reading, you'll have a full grasp of the exploration of Mars, past, present, and future. So before we talk about the actual exploration, I do want to go into some basics about Mars. The readings of the terrestrial planets, which I think you'll be doing any time now, cover off some of the basics of Mars and Venus and Mercury. And you'll also hear those discussed in all the other materials where Mars is touched on. But I want to make sure you have some of the basics kind of well understood about Mars. It is the most Earth-like planet in some ways, and it has some features that are relatable in certain ways. But of course, being a planet where there's no life, there's no vegetation, there's no anything like that, it is very, very different. And of course, there's no oceans. But we'll come back to the ocean question. A major thing with Mars is this major geological divide that you see really from space. If you're observing Mars from a spaceship as you approached it, you might make out something relatively obvious, which is that the southern hemisphere is heavily cratered and almost moon-like or Mercury-like in its superficial appearance. There's lots of craters, there's lots of rocks, lots of cliff faces, things like that. It's a kind of unforgiving territory that we're used to, certainly with the moon. Um, the north is much lower altitude. It's much smoother, and this, if you're paying attention, may be a result of a past on Mars that was very, very wet, and a past on Mars where there were oceans. And if there were ever oceans on Mars, and Mars ever did look like the Earth, um, the watery bits, the watery parts, would have been in the north. So on Earth, the water is kind of spread out relatively evenly. It's more in the southern hemisphere, but there's ocean everywhere. Mars would have had pretty much mostly ocean in the northern hemisphere, and then a small sea in the southern hemisphere, in what we now call Hellas Planitia. But other than that, the the divide would have been quite drastic. Um, so two other features I want to talk about with Mars. One, Olympus Mons, which you may have heard of. It's the largest volcano and arguably the largest mountain in the solar system. So it is a gigantic volcano on the surface of Mars. It'll come up, I think, later on. And then there is Valles Marineris. Valles Marineris is a large um, canyon-like feature on the surface of Mars, but to call it a canyon may be a bit of a misnomer. A canyon is a terrestrial term for a water-carved feature, and of course the Grand Canyon is a very, very large one of those. Um, Valles Marineris is often compared to the Grand Canyon, but the difference is that more likely than not, Valles Marineris is a tectonic feature or a structural feature of the planet caused by tectonic movement, and not in the sense of tectonic plates, because Mars doesn't have those, but in the sense of volcanic activity and seismic activity. So, sorry, I have an injury and I can't move my wrist on my left hand. So in that sense, while it's often kind of talked about as Mars's Grand Canyon, it's much larger than the Grand Canyon. It's the size of the continental United States from east to west on Mars, and you see it there in the bottom. But it's not a water-carved feature. It is more likely than not a fracture. Couple other things about Mars that are helpful to think about before we talk about some of the missions that found these things. Mars does have polar ice caps, so like Earth for now, there are polar ice caps at the poles of Mars, and these do, like Earth, shrink and expand with the seasons. So also, if you remember from week 2, Mars has an axial tilt very similar to the Earth's. That provides its seasons, and with seasons come changes to the radiation budget, and with changes to the radiation budget comes changes to a planet's surface and its surface features, its atmosphere, all of that stuff. So Mars has polar ice caps that do shift with seasons. It has a very, very thin atmosphere. So Mars is, though Earth-like in some ways in terms of size and having seasons and somewhat moderate temperatures, it barely has an atmosphere. And for the sake of humans, it really has no atmosphere. It would be far thinner than even the top of Mount Everest. It would be far thinner than even where commercial airlines fly. It's an atmosphere that is about 10% that of the surface of the Earth, and is obviously lacking one very important feature, which is oxygen. So even if it were thicker, it does not have oxygen, a key component to humans being able to move about freely without a spacesuit. Compared to Earth, Mars is quite dry and inactive. When we talked about the moon, we talked about the moon being very, very inactive and dry as well. Compared to the moon, Mars is quite lively. It has dunes, it has wind, it has polar ice caps that change, it has ice just below the surface that is melting and maybe giving off moisture. It has all sorts of things happening compared certainly to the moon and Mercury, but compared to Earth, it's far more desolate than even the most desolate desert on Earth. And compared to Venus, though we don't have a great sense of what's happening on the surface of Venus, it's also quite tame compared to Venus. But again, not being as extreme as Venus, it is much more interesting to people because we can get robots on the surface and hypothetically one day in the future, maybe even humans. There is evidence of relatively recent, and by recent I mean geologically recent, and so that means millions of years, potentially less than millions of years, hundreds of thousands, in terms of certain things happening. Geological activity like volcanic eruptions, those probably less likely, and the presence of water, I guess both of these quite less likely to be within the tens of thousands or hundreds of thousands, but certainly within the last millions, tens of millions. These things have happened, or the evidence for them is there and present on Mars, but we certainly don't see them today. But that they've happened certainly much more recently than they happened on the moon is, again, something that makes Mars interesting. And we'll talk about this with quite a few missions, and you'll notice a trend in pretty much all of the missions. A big focus is on water. Is there water on Mars right now? Now we know on the surface there's not a ton of it sitting around. There's no visible water, just in the sense that Earth has visible water. But are there very, very small concentrations of water just underground? Is there ice that maybe peaks to the surface and melts for a bit and then evaporates away? This is an ongoing question. You'll see some of the missions that we talk about, especially the more recent ones, really engaging this question of water and getting into these salty brines that may exist and these seasonal features that may exist. And there is evidence of what have been identified as, or called in fancy terms, recurring slope lineae, which is a potential presence of surface water for a very, very brief time that would melt from some underground or undersurface, subsurface ice and present itself on the surface as briny-ish, water-ish stuff for a very, very short period and then evaporate away due both to the lack of air pressure to keep it in liquid form and at times solar radiation. So yeah, let's move on from here to our first mission. So there isn't a ton to say about the Soviet Mars program. Arguably, it's a footnote to history with the slight exception that it is the first thing of human creation to touch Mars. So that is one, I guess, feather in its cap. But the Mars program was a series of landers and orbiters in the 1960s and 70s. So again, smack in the dab of that space race. Mars 2 crashed into Mars, but was, again, I guess, successful in touching Mars. Mars 3 was the first object to land on Mars in December of 1971. Now, it landed, but unfortunately, none of its instruments really worked. It may have taken a picture. My air quotes aren't in the frame there. I once upon a time was under the impression that it was an image, but it's more likely than not just a bunch of messy data presented in pixels, which is hard to really call an image. Mars 5 was a successful orbiter, but no real significant data to discuss. 4, 6, and 7 all failed. Now, you don't really hear about the Soviet Mars program too often. The Soviets, by this time, had shifted some of their focus. Their Venus program was much more successful than their Mars program, and they were certainly overshadowed by the Mariner program as well. So between Venus and the Moon with the Lunokhod and Luna programs, Mars is kind of the less remembered aspect of Soviet exploration of Mars, of the solar system, I should say. But, you know, a notable first with the first soft landing of a spacecraft on Mars. Fortunately, they couldn't follow that up with any useful information, but nonetheless, a first, the first country on Mars, so to speak. So far more often you'll hear about the NASA Mariner program as kind of the earliest days of Mars exploration. There was also the Pioneer program, which would have flown by, but we'll focus on the Mariners. The Mariner program had a series of successful flybys. You see here, Mariners 3, 4, 6, and 7. Flybys at the time were a big deal. They took images as they flew past. As you can see in the bottom left corner, they'd get those kinds of images with not great cameras. They're pretty simple probes. But Mariner 9 was able to enter orbit into orbit of Mars, which was a bigger deal. That was able to provide multiple images of the surface of Mars as it went around, which was a first. So being able to orbit a planet is far more, obviously, far more important than just flying by, because you can get multiple images and try to image the entire thing. Yeah, the Mariner 9 image you see in the bottom left is the kind of image that all of them would have got, although the Mariner ones were a little bit more close up because they entered into orbit. But as you can see, we've come a long way in terms of image quality from orbiters, landers, rovers, of course, and even flybys. As we'll talk in a couple weeks about the exploration of Pluto, which we've only done through flyby, but those images are far beyond anything that was imaged by the early Mariners in their flyby of Mars.
In exploration, there are great moments of success and moments of setback. Lasting memories forever etched in our combined experience that forge a stronger resolve to reach new heights and explore the unknown. As we gaze off into the solar system, something in our humanity pushes us to move forward. We began as wanderers, and we are wanderers still. We have lingered long enough on the shores of the cosmic ocean. We are ready at last to set sail for the stars.
And liftoff of the Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
NASA has been on a journey of exploration for more than half a century. A journey to Mars. From Mariner to Phoenix, from Curiosity to Maven and beyond. We've placed the marks of human exploration and ingenuity on and around the Red Planet. "40 years ago, NASA's Viking project found its place in history. July 20th, 1976. Viking 1 was the first human probe to land on the surface, return images and data, and conduct science experiments on Mars. Viking was a bold step for its time and a huge undertaking for NASA. NASA employees, contractors, and industry across the country designed the elements of this project. Viking consisted of 2 identical spacecraft, with a payload of a lander and an orbiter in each. Viking 1 and 2 were launched in August and September of 1975. Each orbiter-lander pair flew together and entered Mars orbit. The landers then separated and descended to the planet's surface for their planned 90-day missions. Viking 1 was originally targeted to land on July 4th, 1976, our nation's bicentennial. But images from the orbiter showed the planned landing site to be too rocky. After reconsidering the options, a new site was selected, and Viking 1 touched down on July 20th, 7 years to the day after the Apollo 11 crew touched down on the moon. The landers took photographs and collected science data on the Martian surface. The scientific consensus from the Viking experiments was that Mars is self-sterilizing due to the solar ultraviolet radiation, extreme dryness of the soil, and the oxidizing nature of the soil chemistry. The search for life on Mars came up empty. But valuable data about Mars, both from the surface and from the orbit, was gathered. The orbiter-lander duos outpaced their 90-day missions, with the 4 spacecraft operating between 2 and 6 years. The Viking 1 lander was the longest-lived of the group, making its final transmission to Earth on November 11, 1982. Today, our orbiters and rovers have changed the way we look at Mars and continue to make unprecedented scientific discoveries, while also answering long-held questions about Mars and its relationship to Earth, our solar system, and beyond. We are working hard to develop the systems and technologies humankind will use to one day live and work on the Red Planet and safely return home. If I have seen further, it is by standing upon the shoulders of giants. The eventual first human footsteps on Mars have as their stepping stones the vital robotic explorers that paved the way for our journey to Mars.
So yeah, there you see the legacy of the Viking missions, or the Viking program, I should say, launched. The first one's in 1975, and their science goals were much more advanced than anything we saw from the Mariner program, because they were going to not only enter orbit around Mars, but also send down landers that would have robotic arms, as you can see in the top image there, and color cameras that you can see in the bottom image there, or at least cameras with the capability of capturing spectra that would give us an indication of the colors on the surface. Calling them color cameras might be a stretch. So the science goals were to photograph the Martian surface, collect data on the composite of the atmosphere, and search for any evidence of life on Mars. So a couple of things to talk about here. That photograph on the surface of Mars was, of course, the first one. And what was big about that was that once it was color corrected based on the data from the pixels that were sent back, the it had answered kind of pretty significant questions about the surface of Mars that now seem almost silly, but were real questions at the time. What would the atmosphere look like in terms of opacity? Would you be able to kind of see clearly? Would it be dusty and stuff like that? What color would the sky be? Would it be blue like Earth, or orangey or hazy? We see here then Mars is typical color correction to what a human would see, is has an orange-ish sky, and would there be any evidence of any biological features? So weeds, grass, bugs would be quite a big one. But at the time, imagery of the surface of Mars had not existed. So while the data from the Mariner and the Viking probe as it approached didn't send back spectral evidence of life in abundance, it didn't rule it out either. And it wasn't until we got down to the surface to start to see that, okay, Mars kind of looks like the moon, but red, and maybe in places less cratery. The robotic arm there that you see, a relatively crude version of up above, was able to sample the soil. It did this in a number of ways. One of the most famous was that it created a chemical reaction that burned up the soil and then measured the materials that came from that chemical reaction, so the smoke, if you will. And one of the arguments once made and continued to be made by a very, very small minority of people in the planetary science community is that actually that smoke that was measured did contain organic material, so evidence of organic material, the building blocks of life on Earth. Most people don't think that that is necessarily the case, and that the signal is not, how should I put this? The signal is not reflective of organic materials or chemistry or a chemical reaction of organic materials, but what you would expect with the materials seen on Mars, iron, silicate, stuff like that. So they landed for America's Centennial in 1976, and both operated into the early 1980s. There were two of them, Viking 1 and 2. Both missions had an orbiter and a lander. At the top there is a earthbound model of Viking. Probably that one's probably used for like museums and stuff, but for all of these missions there is Earth versions for the engineers back on Earth to kind of play with, to see they try to recreate all of the conditions that the lander in this case are actually on, and then if something's not working they go to the model and see, okay, what could it be? If there's sand in this joint, is that what's happening? And they play around rather than try to figure out something a few 100 million miles away. They play with the model just at NASA JPL in this case. And yes, the bottom is the first color image from Mars. I guess worth pointing out, you'll see the two landing sites of Viking 1 and Viking 2 here, different areas of the planet. This image may be, or this kind of map projection may be unfamiliar to you, but don't worry about that. It's essentially representing a sphere, and just showing that Vikings landed both in the mid-latitudes, so in an easier area of a planetary body to land. It's more difficult to land at the poles for gravitational reasons, but and for maneuvering reasons, so engineering and gravity. But this is, I guess, worth giving the reminder that these missions are all picking, with the exception of the rovers that move, pinpoints of Mars in different places. You see there also the Pathfinder mission, which would be chronologically next after Viking 2 in terms of touching down on the surface of Mars. We won't talk about Pathfinder, but it was a lander and a very small experimental rover called Sojourner. And for a long time, these were the three missions that had landed on the surface of Mars, and their kind of global coverage. So you'll see there's another version of this later, I think, with all the missions, showing how that is kind of filled out, and we've started to move towards more of the poles, but also filled in some of those areas that don't have anything when there's only three landers across an entire planet, 1/4 the size of the Earth. A few other findings from the Vikings that are worth talking about. Again, pretty much anything Viking saw was a revelation because it was the first lander. So even something as simple as acknowledging that there were daily Martian weather changes was, again, certainly something that could be foreseen and known from a distance, but observing them in real time for a first really hammers down, how active are they, how active are the wind gusts, even though we know that the atmosphere is very, very thin. The landers would have had an opportunity to provide more information on to what extent there is an atmosphere, what it's made up of in some cases, and how much it moves around. And does it move around, sand on a certain scale? Does it create new dunes over the period of a week, a month, a year? That kind of stuff. And then, of course, because they were able to touch the Martian soil, they were able to identify mostly what it was made of. As I talked about, the Viking biological experiments, as they're known, have been revisited and debated periodically over and over again for the last 40 plus years. But it's safe to say that we have much better data now, and the likelihood that that one mission somehow landed in a spot with organics when multiple other missions since then have not, is adding fuel to the fire that it was either a false negative or misinterpretation of the data. That robotic arm also had kind of a scoop on it, like an old school, like at the playground, like it's just a scoop, which was able to just pull through and identify some of the soil underneath the topsoil or the surface, indicating, was there any moisture immediately under the surface? There was not, but later on, actually, the Spirit rover did identify that immediately under where it was, there was ice. So, Viking didn't hit that, but later missions. So yes, after a relatively quiet 1980s and 1990s, we returned to Mars, we being Earth, in the early 2000s with a vengeance with the Mars exploration rovers, the MERS, Spirit and Opportunity, both launched in 2003 by NASA. They operated for quite a while. Spirit turned into a lander, unfortunately. After about 6 years of operation, it got stuck. It still operated kind of intermittently until 2011, when it couldn't be made contact with. More likely than not, dust began to cover its solar panels, which you can see in the bottom left image, in the rover image. And it was unable to generate enough power to stay operational. Opportunity was a marathon runner, so to speak, operating until 2018, so 15 years of rover operations, by far the longest operations of any rover, and likely to stay that way, although Mars Curiosity is already at year 12, so it's catching up. And a ton of images from these rovers. Too many findings to really talk about in detail here, but we'll talk about some of the big ones. Again, just a reminder, as these missions pick up, we begin to cover more of the surface. This is the more traditional representation of Mars in a 2D form or as a globe. So this is the equivalent of a world map for Earth that you would typically see. So North America would be in the top left there, and Asia in the top right, as with most European-centric map projections. This is the equivalent for Mars, and so that we can go back to also the earlier discussion about the northern hemisphere being much lower altitude. You can see that with the blue. You can also see essentially where the ocean would have been, which is conveniently colored blue, but that's not to represent water, that's just to represent low altitude. And then you can also see Hellas Planitia there, which would have been a sea full of water as well, if Mars were ever that wet. You see the Tharsis Mons here, which is a series of 3 volcanoes. You see Olympus Mons right here, Viking Lander 1, Viking Lander 2, and then Opportunity and Spirit. So, you know, if this were Earth, this is maybe the western side of Africa. This is, well, really the middle of the Pacific Ocean. But yeah, so they're quite far and away from one another, but again, very close to the equator of Mars. Again, that makes things a bit easier for the engineers, but that's changing these days too. This image is not from one of the Mars rovers, obviously. It's of one of the Mars rovers. You can see circled there, Spirit near Bonneville Crater. Imaged by HiRISE, which we'll talk about next, which is the kind of the top end orbiter orbiting Mars since 2005. But you know, this kind of helps represent that all these missions, when they're there at the same time, and certainly if they're there being operated by the same space agency like NASA, they'll typically work together, but well, they won't typically work together. They do work together. They're part of a larger kind of exploration infrastructure where the imagers on these orbiters provide kind of aerial views of where these things are and where they're going. Obviously not in great enough detail to drive the rover. You need the rover to have cameras to do that. And the rovers kind of help confirm the analysis done by orbiters that use spectral data bounced off the surface of the Earth, of Mars to indicate what the materials may be. What else was I going to say about this? Yeah, and also I should say, you know, all the missions work together. So whether it's a Chinese space mission, a European space mission, a Russian, a Canadian, the science teams of these missions tend to work together and share data so that all the missions can be as successful as possible. As I said, the rovers have cameras on board them as well, obviously. And this is not necessarily a typical image just from the forward cam. This is a panoramic view, so this is a stitching together, and you can actually see the stitch marks if you look closely of the camera, the panoramic camera, so the cameras on the mast of the rover spinning around in 360 degrees and taking images. And this shows a portion of the landscape ahead or perhaps behind, based on the instruments. That looks like ahead of Opportunity as it approaches Cape Tribulation. So these kinds of panoramic images are both used by the rover team to do two things. The engineering team looks at this and say, are there any obvious hazards ahead, and how does this affect our kind of path forward? The science team looks at this and says, okay, are there any interesting targets ahead? And those two processes can conflict, because something really interesting might be somewhere dangerous from the rover's perspective, or it may be just out of reach of the rover, or it may require too much energy to go there compared to something else. So these are kinds of discussions that take place within rover operations teams. You have the engineers who are first and foremost concerned with the health of the rover and ensuring that it meets its objectives, its primary objectives, and then any secondary mission objectives, and the scientists who are aiming at finding the most interesting stuff and approaching it as close as possible, ideally even touching it. But that's not always possible, right? A really, really interesting feature may be identified, but it may be too close to a slope that could trap the rover, that could damage one of the rover's instruments or anything like that. I guess last but not least, The rovers will look behind themselves. So this is a more typical image, although this is still a stitching of multiple images together. But the rover will look behind itself. One, it looks cool, but two, there is some useful information from this. You can see in the tracks if there's any sort of problems with the way the rover's wheels are turning. So if there's any drag, or if there's, well, yeah, obviously if there's any pieces of the rover behind, that would be a big problem. And you may think that's silly, but the Mars Curiosity rover had pieces of its wheels being damaged and falling off. So, these are the kinds of things that if you look behind yourself as a rover team, you would identify. But yeah, I mean, there's, I guess there would be science objectives here too, just in case you happen to drive past something you didn't notice while you were looking. And looking backwards, if a rover turns, may provide a new perspective. But I imagine, quite often these wheel tracks are just kind of quickly analyzed just to make sure there's nothing abnormal in the kind of pattern of the wheels. The wheels do have kind of pretty distinct ways of turning, and they should leave these, as you see, these tracks that have ridges in them every once in a while. That indicates the wheel's turning just fine, at least to my eyes. I don't remember Opportunity ever having major wheel issues. So combined, what did these two rovers do? And I guess just as I was going to say, because I was going to call them two little rovers, and then I realized maybe you don't have a frame of reference for the size of these. So the Mir rovers were the size of, what's a good comparison? And what do they often compare to? I don't know, for some reason a vending machine comes to mind if you tipped it over, ballpark, though that's a little bit long. But around that size. So like bigger than a kid's Power Wheels, but smaller than a small car because well, a really small car. The wheelbase wasn't the same. Anyways, I hope you get the picture. So one of the cool things that the Mars exploration rovers identified through images was dust devils, which are like, tiny little tornadoes. You may have seen them if you're ever walking in an urban environment. There'll be little wind traps happen, and leaves and garbage will get spun up in a little dust devil. They saw them on Mars, and in the top right image there, that actually helped identify the tracks of these things across the Martian features by orbiters. Their findings, especially spirits, because it interacted with ice, suggested at the time more evidence towards water on Mars. And I say at the time because by now in 2024, saying evidence for water on Mars is almost a meme because it's said so often. But in 2009, or I should say probably 2005, it was actually a much more interesting headline for an article than it has been ever since. And that likely because of some of the observations of materials that the water and lava would have interacted on the surface of Mars, so indicating that volcanic activity and a wet surface coexisted, helping maybe to constrain when each of those happened, although if they both happen at the same time, it doesn't necessarily help. So they overall added to the wet Mars hypothesis. So if you've ever seen images of, you won't believe what Mars looked like 2 billion years ago, there's some truth to that you'll see image of Mars with oceans and I hope not plants, because we don't know that ever took place. But that kind of idea of Mars being an ocean world really kind of took off in the 2000s because of this, because of the rovers didn't absolutely confirm that Mars had oceans. In fact, to this day, there is ongoing debate about that. But they certainly didn't rule it out, and they certainly added to the evidence that there are all of the features that you would associate with a lot of water that the rovers encountered were there, I should say. So the rovers added to that kind of hypothesis. So a lot of these images that I've been showing are actually from a single spacecraft, the Mars Reconnaissance Orbiter. There's other orbiters above the surface of Mars, as you'll hear about in the podcast and in readings, but MRO is really the main one I want to talk about. It launched in 2005, and it provides high definition images of the Martian surface with its high resolution imaging science experiment, HiRISE. HiRISE goes through cycles where it targets things, captures them, and sends them back to Earth. One of those cycles has historically been operated out of Western, so that's neat. You know, a Mars mission, a Mars instrument being operated out of Western University. And it uses a spectrometer to study the composition of the surface materials. So this hasn't been explained elsewhere, and if you're not of geology or physics or chemistry background, quite rapidly, I guess I'll say, is spectroscopy very basically is just measuring how light bounces off of something. And the way light bounces off things is unique to the materials making up those things. And we essentially have a catalog of the way light bounces off of everything on Earth. So then when we see light, and by say bouncing off, I'll explain that in a second. When we see light reflecting off of a material elsewhere, if that matches the way it does it on Earth, we can be confident that those two things are the same materials. And the way, I guess I should be clear about bouncing off or reflecting. So when a wave of light strikes my mug, some of it is absorbed by the mug, some of it bounces off. So the some that bounces off could be captured by an instrument, and let's say you have a band, and some of the wavelengths were captured by the mug and others were released. The ones that were released are that spectral fingerprint for the materials that make up that mug. Is the kind of crudest I can put it. So that's the basics of spectroscopy, and that is what allows us to understand what something we don't touch is made out of. Our eyes kind of do this. So, you know, you may see something and know what it's made out of, even if you don't touch it. And really all you're doing there is kind of a version of spectroscopy, sort of, where, you know, you're looking at the object if you're a sighted person and you see, uh, you know, it looks familiar to you. So based on your previous experience with materials, you can make a good guess of what that is based on how you're seeing it, which is really just light bouncing off of it. And again, that's a crude way, and I was distracted, sorry about my cat entering, a crude way of describing spectroscopy. And that's the basis of MRO. It also has an infrared sounder to analyze the Martian atmosphere and a sounding radar. So these are just pulses of information sent down to the surface of Mars and bounce back to the spacecraft. And again, based on the way they bounce back and how long they take and how much they're distorted, gives you information about the atmosphere, its opacity, its composition, its temperature, stuff like that. It has a context camera for bigger images with less resolution. And MRO is the one that discovered those things I talked about earlier, those recurring slope lineae, which is the potential of subsurface ice melting and sublimating to the top and then evaporating away. But in the process, that would imply that liquid water was on the surface of Mars at one point. In very, like right now, I should say. Like that's the interesting part about it, is that it's happening right now, which means hypothetically there's liquid water on the surface of Mars in very, very tiny amounts for a very, very short period. But still, interesting. Hi. The other thing the orbiters are used for is traverse mapping. So you can see here the traverse map for opportunity. So this is done on a regular basis. This one is quite, it's not very granular. It's quite coarse, but it shows where the rover goes, where it stops, and does some science for a couple of days, or even some new decisions about which way to go, and then it moves again, and it's all tracked by Sol, which is the term for a Martian day, which is roughly twice the length of an Earth day, and so yeah, at Sol 1 would be the first day of the mission. Sol 2 would be the second Martian day of the mission. Sol 3 would be the third Martian day of the mission. So you can see there, if you could make out the resolution. I'm sitting on my mouse. You can make out, how the rover has moved based on different days and how long it has stayed at different things. But these orbital images are used to help understand the wider context of where the rover is and where it's been. This is an enhanced color image from the HiRISE mission. It's also just a really pretty image of a crater in Sirium Fossae. And I want to just talk about, why you sometimes see images of Mars that are blue or green. That's not what our eyes would see. Essentially, enhanced in this case means that the contrast is turned way up. So you can do this, well, more on old TVs. I guess you could do it on new TVs too, or on your laptop, where you play with the contrast of the screen or a video file, and things will rapidly change. So things that your eyes wouldn't otherwise see, if you turn up the contrast or you emphasize certain things, they become more vibrant than our eyes typically see. So one way of saying it is that blue is kind of always there. It's just our eyeballs don't see it. It's a reflection of a certain kind of light that we don't see, or it's an enhancement of a material that's there that is so faint that our eyes don't see it. So yeah, so just to remember with space exploration that images are often done like this, because if you didn't enhance the color, everything would just be orange. But if you enhance it and you ramp it up, you can see that there is a distinction in the materials and what they look like and how they're reflecting light. Now this is extremely enhanced because you have blue, but it still helps us understand that, okay, there's different materials in one region versus the other. Something is happening there. Nothing radical, it would be radical if this is what it looked like to our eyes, because that would indicate very strong concentrations. But more often than not, it's just shown to show that there is difference, that there is a distinction. For instance, a lot of images of the moon because there isn't a ton of geological variability. Well, there still is in most cases, but a very simple environment where there's almost all a few basic elements. It doesn't matter how much you turn up the contrast, it wouldn't change, but that's not the case on Mars and on most planets.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage it's in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
So the Mars exploration rovers in 2003 landed via Bouncy Bounce. Mars Science Laboratory, MSL, also known as Curiosity, it landed via the Sky Crane. Well, the parachute and the Sky Crane, as you see in the graphic here. Its overall goal is to understand the potential for life on Mars by studying surface processes, weather, climate, essentially everything we've been talking about. It's just a bigger and better rover than Spirit and Opportunity. And a main focus is an exploration for organic chemicals that are the building blocks of life, and things like methane. So this is Curiosity. It's one of its selfies, so to speak. And this is done by the robotic arm on the camera, or the camera on the robotic arm reaching out and taking a picture, just like humans take a selfie, and then it's kind of touched up so that you don't see the shadow of the arm and stuff like that. But nonetheless, this is a very famous image of Curiosity. It's well into its mission here because there's dust all over it, and its wheels are already beat up, as you can see. But yeah, you can see it's also in pretty hazardous terrain in some ways, I would say. You see, there's rocks. Also worth noting, so yeah, Curiosity is huge. It's the size of a small SUV, so it is a much bigger rover than Spirit and Opportunity. A ton of instruments on Spirit. We won't go through them all. The instrument suite on board, again, was a ramp up of what had been done on Spirit and Opportunity. A couple things just to point out. You'll see front has cams, rear has cams. Obviously, these rovers have cameras trying to point all directions to identify, like the case in this, not image, but animation, the rock right in front of it, which is not something you'd want to drive into, but is something you'd want to drive up to. And then you have the robotic arm with a number of instruments on board. The APXS instrument is a Canadian instrument operated out of York University. You have a series of sample analysis, SAM and Chemin instruments, ChemCam, which is a spectrometer, NavCams, again for navigation, the MastCam, which is kind of a all-purpose camera, but certainly helps identify its terrain ahead of it, and then a series of other kind of communications and analysis instruments. So that's MSL in a nutshell. I do have an entire podcast, not about this rover, about the follow-up Perseverance and all of its instruments, where I talk with one of the lead engineers of Perseverance about the instruments on board Perseverance. It was recorded before Perseverance launched, so I don't really use it anymore, but it is on the 2090 YouTube page called Driving a Mars Rover, if you're interested. We go into more detail about what all these instruments do. I won't go into great detail about all of the objectives of MSL because there are a ton. It's a quite complex mission, but I should say that at the end of the day, all of these missions kind of have the same overall objective, with a few interesting additions and nuances, especially with Perseverance, where you have kind of the MOXIE instrument and the microphone. But with this one, it's all kind of the same thing that we've been doing since Viking, looking for evidence of water, looking for evidence of organics. There's other stuff, measuring the level of surface radiation. That's relatively new, not something that was specifically a focus for previous missions. An important one if humans were ever to go to Mars, because not only is there no atmosphere, it's a significant dose of radiation every second. So it's, if we do ever send humans, you'd want to know exactly how much radiation they're in for, and what kind of materials would need to be used for any sort of base camp and spacesuits. But yeah, I won't go into all of these. You can read these on your own. But just to say that, with each of these missions, the complexity increases, as do the number of objectives that they have. Again, if this were a planetary geology course, there'd be hundreds or maybe dozens of findings to talk about with MSL. I'll just talk about some key ones, although contentious. What's called a methane spike in the instruments was discovered, maybe discovered in 2003. And again in 2014. So no consistent pattern of methane being discovered by Curiosity since it's landed. And also since that period, there's been an entire orbiter sent to Mars to try and find methane, and it hasn't really. So this is again debated because the nature of that data can be interpreted in multiple different ways. But that's kind of one of the big takeaways for MSL. It's continuing its mission to this day, uploading hundreds of images to NASA's website every month. It's done a ton of work. It's used its robotic arm to kind of abrase rocks and see what's just underneath. So like brush them with a kind of a powerful brush, and kind of zap them with a laser-induced breakdown spectrometer, a LIBS, to identify if there's any kind of outlier rocks lying around. I don't want to undersell what MSL has done, but I do want to not focus too much on individual findings, just to say that MSL more so just reinforced what the Mars exploration rovers hinted at and indicated, but it hasn't led to any earth-shattering discoveries, certainly about Mars, but has significantly advanced our understanding of Mars. And everything I talked about at the top of this lecture, all of that either confirmed or enhanced or directly found by the MSL mission. We can talk about methane one last time, because so you can see here in the image there's outgassing, which is hypothesized to be kind of what happened if there is methane on Mars. It's subsurface, and it's finds its way to the surface through seeps and cracks, and it's possible that the rover drove over one of those and its instruments picked up this methane. Now, the debatable part about this is that methane can be formed biotically or abiotically, and that is to say, it can be the result of organic materials decaying, which happens on Earth constantly, but it can also be the result of a completely non-biological chemical process, with rocks like olivine breaking down through a basic chemical process that has nothing to do with organic material or that has nothing to do with life, I should say. So even if the methane data is accurate, which absolutely could be, and I'm of no qualification to assess that data. Even if it is, it doesn't necessarily mean that methane is the result of organic or biological processes. It may just be abiological processes.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
So there were two videos there. One, the actual day of the landing for Perseverance, which I remember was quite cool because a lot of those images of the parachute deploying and all that were being uploaded to Twitter like, instantaneously, and that was neat. Because when MSL landed, social media was around 2012, but not a lot of people were on it, or I should say, not a lot of scientists were on it at the time. It was still relatively early. And the same kind of community of sharing information as missions happen wasn't up and about yet. And then the second video was the animation of what the landing, and the animation is older than the first video because it's what they intended to happen, and what they intended to happen did happen. So that's good news. And it was essentially the same landing procedure as MSL. It was parachute to sky crane, and it went well. So that's 2 for 2 on the sky crane. And Perseverance is on the ground, and it's the latest and greatest in rover technology. It's essentially an upgraded version of MSL. And its objectives, again, I won't go through them, but they're a little bit interesting. Actually, I will go through them because they're a little bit different. So looking for habitability, again, past environments, water, evidence of biological processes. Seek biosignatures, again, same thing. So those two are kind of continuation of the last couple decades of Mars exploration. The big difference is this collecting samples with a percussive drill, and then caching those samples in areas that another future mission could pick those samples up. They're in little tubes, collect them, and then return them to Earth. That mission doesn't exist yet, but it's a hypothetical mission. And then the MOXIE instrument is to test if you can produce oxygen in the Martian atmosphere, and they have successfully done this on a very tiny scale. So they take the materials in the Martian atmosphere, concentrate them, and see if they can create oxygen in a larger abundance, and they have been able to do that, again, to a very small scale. Again, Perseverance has, even just in the, oh boy, it's already been like 5 years since it landed, it's done a ton. It did discover volcanic rocks where people didn't think there'd be volcanic rocks, so just some evidence there for some major disruption of volcanic materials in the relatively recent past. It sampled ancient lake beds, which hadn't been done yet before. And it, I already mentioned the MOXIE instrument successfully produced oxygen on Mars, and then it listened. So if you do listen to the podcast with Raymond Francis, the lead science engineer, or co-lead science engineer for Mars Perseverance, he talks about why you would have a microphone on Mars. I'll give you a couple of seconds to think about what scientific value you could get from it, other than it's cool to hear what's happening on Mars. What would you hear? Just give you 5 seconds while I try to move my arm, which is still very, very sore. So 2 things immediately come to mind. 3 things, come to mind based on my knowledge of this instrument. One of them is to listen to wind, which gives you evidence of wind velocity. So a microphone is a good way to measure wind velocity, because the more powerful the wind, the louder the sound waves, the louder the data. The second thing is that you could have the microphone running while you operate certain functions of the rover to hear how the arm is moving, the wheels are turning, stuff like that. The third one, which I wasn't aware of until I talked to Raymond, was that the laser-induced breakdown spectrometer essentially breaks rocks with lasers. And the way that rocks break or pop gives off a sound, because there's an atmosphere, thankfully. And that sound is indicative also of what materials that rock may be made out of. So there's not just engineering and meteorological value to that microphone, but also geological, which I didn't know was a function. Perseverance has collected a ton of samples through its first few years on Mars, and it's cached them about for, again, a future mission to come pick them up and send them back to Earth that mission TBD, to be determined.
And liftoff, launching the next generation of robotic explorers to the Red Planet.
We'd made it through launch, cruise, EDL, all of that, and we were ready now to begin our real mission, our real life on Mars. And we were all excited to see what Ingenuity could really do. So we were ready for Flight 1.
Earlier today, Ingenuity should have autonomously performed its first flight attempt on Mars.
We were all holding our breath.
Ingenuity is reporting. Altimeter data confirms that Ingenuity has performed its first flight of a powered aircraft to another planet.
At that point, you just open the floodgates of what is possible.
Yeah, it was surreal.
That was the crowning achievement of the team.
You know, we really had to hold hands and do it together.
From that moment forward, really, we were off to the races and saying, okay, great, that's done. Let's get back to work. Let's get to Flight 2, and then 3, and then so on and so on. How fast can we fly? How high up above the surface can we fly? We started doing things in parallel with the rover, and we've also demonstrated that the helicopter can be a scout to help scientists. It's been a remarkable journey, and I think a highlight of all of our lives to have been a part of it.
Of course, there's a little sadness that, oh no, it's over. It's kind of the end of an era, but it's also the beginning of an era.
To realize, you know, what you're part of here, at least for me, I kind of get goosebumps.
We hope that Ingenuity will inspire teams to build larger, more capable vehicles. From a science perspective, what is interesting now that we've unlocked that aerial dimension?
The best way to predict the future is to create it.
China has successfully landed its first rover on Mars. The Tianwen-1 lander touched the planet's surface after surviving the treacherous descent by parachute. China's President Xi called the landing an outstanding achievement and said the scientists had placed China in the advanced ranks of planetary exploration. Michael Bristow reports.
Only 2 other nations have reached the Red Planet, the United States and Russia. So there was understandable apprehension among Chinese scientists. The landing craft entered the Martian atmosphere in a protective capsule, then parachuted towards the surface. Earth is too far away to control this delicate process. The rover was on its own. Rockets slowed the descent further before the final part of this 10-month journey, touchdown. The 6-wheeled landing craft named Zhurong then opened its solar panels and sent back a signal to Earth. Back in China, there was relief, joy and celebration. This is the country's first mission to Mars.
It should be said that this was not an easy task. It is our first time down this path and we have met many difficulties.
The rover will spend 3 months collecting data. China is now undoubtedly one of the world's leading nations in interplanetary exploration. But the Chinese are not the only ones interested in Mars. In February, the US rover Perseverance made a successful landing there. Competition between these 2 leading nations now extends millions of kilometres into space. Michael Bristow, BBC News.
Last but not least, Zhurong. It was an active rover up until this last summer, but it was China's first mission to Mars, and the Zhurong rover, as you can see there, and that's an actual image next to the lander it drove down from, that had a little ramp, and it arrived there on the Tianwen 1 orbiter, and it operated for about 2 years, if I'm not mistaken. Sorry. Completely blanking on that. But the mission had very clear objectives, very similar to, again, everything we've talked about, but had more kind of atmospheric and I guess, kind of weather focus, to study the Martian physical fields, electromagnetic, gravitational, and internal structure. It also had a radar on board, as does Perseverance, to look for subsurface water concentrations. Yeah, so this picture is actually quite interesting. The rover dropped a little camera on the ground, drove back, and then took an image of itself with that little camera left on the ground. So Zhurong was very successful in its couple years on the surface of Mars. Big findings there. You can see its traverse map, but big finding being potential for further confirmation of that kind of briny water seeping to the surface of Mars. And in this case, creating almost sort of like a crust-like layer on the top levels of the soils, we'll say soils, that the rover was looking at. Yeah, so Zhurong went to sleep in the summer of 2023, and it seems like I won't be able to wake up for the Martian winter that it went to sleep for ever, because its solar panels are probably covered in dust. But nonetheless, very successful mission, very similar in design, though with different instruments to Curiosity. And yeah, that's well, unfortunately not the future of Mars, because Zhurong stopped working. But Curiosity and Perseverance continue on the surface. They're actively orbiters around Mars. MRO continues to be there. Trace Gas Orbiter continues to be in orbit as well. And as is the UAE Mars Orbiter and the India Mangalyaan Orbiter. So lots going on at Mars, lots planned for Mars. Another rover from the European Space Agency. It's been delayed. Only recently we had the NASA InSight mission stop functioning, but overall the future of Mars is more rovers, probably from more countries. India has plans for a rover on Mars, I believe. China has plans to return, and NASA has plans to, with the European Space Agency, send another rover and pick up those samples that Perseverance has cached. So yeah, that's it. As we speak, it's only been a couple of weeks since Ingenuity stopped working, but you saw the video there that I tossed in. So yeah, that's Mars exploration. I hope you enjoyed it, and we'll see you next week.